TaylorMade is a prominent golf company known for its innovation and quality in golf equipment. It was founded in 1979 by Gary Adams, who introduced the metal wood, a groundbreaking design that revolutionized the game. TaylorMade products are favored by many pro golfers, including Tiger Woods, Dustin Johnson, and Rory McIlroy, who have all used TaylorMade clubs to achieve significant victories on the PGA Tour. TaylorMade equipment is used by many pro golfers, and they are number 4 on the PGA Tour with drivers, hybrids, wedges, putters, and golf balls, while being number 5 with irons, according to PGAClubTracker.com. Welcome back to another episode of Polymer E-Clubs Ask Dr. Paul. Today we're going to highlight solubility parameters and environmental stress crack resistance. So when your boss talks about chemical resistance of polymers, what do you need to know? Chemical resistance refers to the ability of a polymer to maintain its integrity and performance when in contact with different chemical substances. The chemical structure of the polymer, the type of chemicals used, and the duration of exposure all play a role in determining a polymer's chemical resistance. On your screen, you see the chemical resistance of filled and unfilled polybutylene terephthalate using chemicals tested at 3 test temperatures. PBT is resistant to many chemicals at room temperature, yet its resistance many times lessens with increasing temperature, and PBT struggles in the presence of chloroform, in which there will be a marked decline in mechanical properties. Chemical uptake is dependent on solvent compatibility, and solubility parameter values of common polymers and solvents are shown, in which similar values yield higher levels of swell or interactions. So polyethylene will swell more in toluene than in water, since they have similar solubility parameter values. Significant swell is common when a polymer and solvent have values within 3 units of each other, and minimal interaction or swell occurs as the solubility parameter delta increases. For containers or housing, it is important that the chemical content inside does not damage the container through staining, yielding, or rupture, and the container plastic does not contaminate the chemical content or product through leaching. Environmental stress crack resistance is a critical property of polymers that describes their ability to resist cracking under stress in the presence of certain chemicals over time. Various factors such as polymer structure, additives, processing condition, and the nature of the stress and chemical environment can influence a polymer's ESCR. Stress cracking pictures are shown on your screen, in which Eastman's Triton copolyester and Treva cellulose perform better than ABS and polycarbonate using a known test torque in the presence of sebum or skin oil, because the oil cracks the ABS and polycarbonate in 2 days, since the given force and chemical creates brittle failure in these samples. An ESCR fixture schematic is shown on your screen, in which the sample is bent over the fixture, causing a known stress and strain, and chemicals are applied and impact strength retention is tested. The table shows that Triton and Treva are superior against impact loss compared to many common plastics using common household chemicals and more. For example, Triton retains impact strength much better than ABS and polycarbonate after these polymers are exposed to Clorox wipes. ESCR measures a plastic's ability to withstand cracking under stress in the presence of certain chemicals. I worked on a high-density polyethylene injection molded part back in the day, in which it was intact out of the mold yet cracked in water. So the change from air to water caused part failure. Wrap your mind around that. And for an explanation, as the water flows across the part, the high-density polyethylene grade cracks through brittle failure due to the built-in part stress from molding, which did not happen in air. As shown on your screen, environmental stress crack resistance is a function of the specific material, stress, and chemical combination. And to improve ESCR, you could choose a more robust high-density polyethylene, and or reduce the molded in stress, and or change the chemical portfolio so the parts will not stress crack. And eventually we were able to make the high-density polyethylene survive a water soak and also handle aggressive chemicals. With many applications, the chemical used and thus the product sold cannot be changed, so we mainly have to work on material selection and molded in stress. In our case, by changing to a higher molecular weight, high density polyethylene grade and working with the molder to diminish molded in stress, the parts survive normal use with the intended chemical portfolio. Understanding stress cracking of polymers is essential for STEM engineers and designers to ensure that the materials chosen will withstand the intended chemical exposures, thereby ensuring the safety and longevity of the products. Knowing about environmental stress crack resistance and how that predicts the chemical resistance of polymers, that's work and knowledge. Remember to like, subscribe, turn on notification, and even share if you appreciate the content. You can visit our website to learn more about our upcoming polymer testing course. I'm Paul Nash for Polymer Close. Ask Dr. Paul. Thanks for watching.